friends, welcome to my another video on Synopsys Sentaurus TCAD. In our previous tutorial video, we have discussed various tools like SDE, SWB and Svisual. Now, the link of these videos I have given in the subscription. In the previous video, I have discussed about Sentaurus Structure Editor, which we call in short form is SDE, which is basically used to build the structure of the device, setting the contacts in the device, giving the doping profile in the device, and meshing. After the structure has been built, we have to simulate this structure using various physics models by solver, applying biasing conditions to the contacts. So all this has been done with the help of Sentaurus TCAD, a tool which is a simulator. That tool we called is Sdevice or Sentaurus Device Simulator. So whatever we have built or whatever device we have created in the SDE has been simulated in the Sdevice. So for that we have to write a command file in the text box or in the text document and save that file as .cmd file, and that cmd file we will use in the device simulator. So let's see how we will use the same file in the CMD simulator. Now, before moving further, I would like to discuss Sentaurus Mesh. What is Sentaurus Mesh? Basically, Structure Editor is the main tool for generating the device boundary file and command files by using Sentaurus Mesh. Sentaurus Mesh is basically a generator of mesh which is 2D and 3D, which create in both aligned axis and tensor meshes, which is used in the simulator that use the box discretization or finite difference time domain methods for spatial device discretization. Sentaurus Mesh also serves as doping profile generator, which allows you to compile 2D and 3D doping profile using both analytical doping profile and numerically simulated doping profiles. So basically, Sentaurus Mesh is worked with the Sentaurus Structure Editor. So how do we build the mesh that we have already seen in the Sentaurus Structure Editor? Now you can easily visualize the mesh in the Svisual or Sentaurus Visual that we have already seen in our previous video of SDE. Basically, the file that is being stored or that is being extracted from the mesh is TDR file. So when you want to open that TDR file, mesh file, you have to write the Svisual file name which has format of .tdr. To visualize the grid in the structure, you have to click on the grid structure, the red arrow which is indicating that how to see the grid structure in the Svisual. So I think this is all about the mesh visualization and Sentaurus Mesh. Now we will discuss about in the Sentaurus device simulator. It is basically a numeric semiconductor device simulator that is capable of simulating the electrical, thermal, optical, and various other parameters of semiconductor device. It simulates the device in 1D, 2-dimensional, and 3-dimensional device behavior over a wide range of operating conditions, including mixed mode circuit simulation, combining numerically simulated devices with their compact modeling, which perform on the spice-based circuit simulation level. So we can see without Sentaurus device, you can't extract any parameters or electrical parameters from the device or the semiconductor device. let's discuss about how to write the command or how to write the command file in the Sentaurus structure editor. A command file is basically in the Sentaurus device consists of several sections, or you can say different blocks are there in the command file. In the coming video, we will see that how to write this command file in the simple manner. So the default extension for this command file is .cmd, like pp1_des.cmd. So if you haven't given this .cmd extension, your file will consider as a normal text document. It will not run on any simulator or the Sdevice simulator. This section defines input and output files of the simulation. So I would like to open the text box in the simulator. Let's see how do we open the text and how to write the command files, input and output files in the text box. So for reference, I have already created a .cmd file, which is a command file, and you can see various sections I have already defined. In the file section, there is a grid file which has TDR extension, plot file which is TDR dat file, parameter file, current file, and output file. So I would like to discuss all these in detail. Let's go to the presentation. The input files is grid is equal to .mesh file. Now we can see it is a mesh file. It is a mesh file. Parameter file is .parameter file, which has all the your material parameters, your input parameters, contains all kind of parameters. Now in the output files, current, plot, and various other types of electrical characteristics you need to specify. So in the file section, we generally provide the input files, which are geometrical structure file, mesh files, and parameter files. And in the output files, we generally provides the output current, plot section, plot file, and output other characteristics files. So all the outputs are stored in these files. The file section and the input section. Sentaurus device expects at least one input file to define the device structure and the field values, which are mandatory doping profile distribution and the optional mechanical stress distribution inside the device. If you have create some stress related device, then you have to provide the mechanical stress distribution in the device file actually. In addition, an optional parameter file can be specified where material properties and physical models are declared. The grid file in TDR format contains the following type of information. Basically, the TDR file is having the various kind of information. First of all, it is a device geometry which contains the region, material specification, contact, mesh definition, including the location of discrete mesh points, also called the nodes and the vertices. Field value in the device, for example, the doping profile distribution inside a device on the given mesh, is also in the TDR format. So it is very important file when you are simulating the device. The grid file can be represent 1D, 2D, or 3D device dimension. It is typically generated by mesh engine Sentaurus Mesh, and file extension.tdr indicate that TDR format is default format produced by the Sentaurus. The optional parameter file includes all the specification of material parameters and user-defined model parameters. Parameters values specified in this file supersede the Sentaurus device built-in defaults. The common extension used for Sentaurus parameter file is .par file. You can just place the file in the containing folder, okay, all the device parameter containing folder, or you can just put the file in the command file. So it will be okay if you are placing the parameter file or the model file in the particular folder in which you are saving all the files. Next is the next are the output files. Now in the figure we can see that model, parameters, sweeps are input files, and device structure is also the input file, and the output files are current.plot file, plot.tdr file, in which you can see the structure, which is simulated structure, and you can see the various parameters, which are current, voltage, potential, electric field, and all the kind of other characteristics. However, the output.log file contains the runtime messages like which command is running or which field is running. So all that type messages are coming in the log file. We have already discussed this. The electrode section basically contains the electrical device contacts are declared in the electrode section together with the initial boundary conditions and other optional specification. This electrode section is very similar to the contact section that we have already set in the SDE contacts while we are creating the geometry of the device. Each electrode defined here must exactly an existing contact name in the grid file. Only the contacts name in the grid section are included in the simulation. So in the electrode section, we name the source, drain, gate, base. In the hemp file, we use hemp gate. In the floating gate devices, we use floating gate. So all the devices have their own name. All the electrodes of device has their own name. Means you can't change the name. If you change the name, it will give the syntax error. So particularly in the contacts, you have to provide the same type of name. Now we can see electrodes. Here we are using the 4 electrodes: source, drain, gate, and substrate. Example of these, we can easily see that if we are sweeping the gate, then we are giving the value voltage 0. minus or 0.5 to the electrode gate. The electrode section also contain the barrier specification like work function. The barrier specification in the gate definition defines the work function as well. So here we are using different kind of materials like semiconductor, metal, and like other polysilicon. So all these have their different work function. So technically we have to define the each work function, but this electrode section automatically define the specified material work function by default. So if we are only we have to give the particular work function for the gate that we are defining for as metal. The current specification in the base definition declares the electrode in the connected to ideal current source and instead of a voltage source, consequently allowing you to ramp the current in the solved section. So if your currents in the current specification, your electrode is connected to the ideal current source, not the voltage source, so which easily ramp the current in the solve section. So now we can see that how the electrode section work and how it is connected to the device in the command file. Now the most important section is physics section. This section declares the physical models to be used in the simulations. These models can be defined globally. Globally means all the models are defined material wise or region wise. So just type physics and list of models that you want to use. If you want to define material wise, then you have to just physics material is equal to material name and list of models. Again, if you want to define region wise, then physics region interface is equal to region name and different set of models. So this section basically includes number of models because we are creating the numerous type of devices and all those have different kind of physics models. So let's see the one example. that is a MOSFET device simulation, in which mobility doping dependent high field E-normal model is used. This model basically specification take into the account for their carrier mobility degradation due to the carrier scattering and ionized impurities. The carrier velocity saturation is calculated with the high field saturation model, and the surface roughness scattering is calculated with E-normal mobility model. So you can see that by just putting these models in the physics section, you can take into the account various type of mobility models and calculate those effects on the device. The next is effective intrinsic density. Now we have to calculate the what kind of effect of effective intrinsic density. Like it activates the band gap narrowing, because we know that whenever we apply some kind of voltage to the device, it will definitely bend the band gap of the particular structure, which is due to the presence of doping, and it is a doping dependent model. So it is, we called it old slot boom model. Now in the MOSFET, we all know that recombination and combination is happens. So for that we use SRH, Auger Avalanche model. So these all are the various basic models that are being used in the MOSFET device simulation. Next is plot section. Now this section specifies the various variable that to be saved in the plot file. Now we have already defined the various models. Now we have what kind of output we want from that particular device. So just write the plot and various plot variables, list of plot variables you can easily see. So we can write like E density, H density, E current, H current, potential, space charge, electric field, E mobility, H mobility, E velocity, H velocity, doping donor concentration, acceptor concentration. So all these quantities will come in the SVisual. So one by one, you can see all these quantity in the SVisual and see the exact value of these quantities. Or you can easily draw the plot just taking the cut line across the device. Now the next step is math section. In the math section controls the simulator numerics. Numerics means in the math section we have to give different type of iterations, number of threads. Your device should be parallelization or multi-CPU machine, or it has very good RAM. Numeric solver controls, extrapolate, derivatives, iterations, relative error control, method, which method you are going to use, not damped method, and transient. Now if you want to use all, you are using all these in one file. So let's see in the math section how we can easily write the commands. This is physics section that we have already discussed. Now physics models, materials, physics in the region, physics in the material interface as well. Plot density. In the plot, temperature, you can also calculate temperature. Field and charges, you can also calculate doping profiles, generation and recombination, driving forces. Driving forces basically E grad quasi-Fermi vector, H grad quasi-Fermi vector, E parallel, H parallel, band gap structure, band gap narrowing, affinity, conduction band, valence band, E quantum potential, and H quantum potential. So all these comes under the plot, and all these if you defined in your, you have already defined in your files, you can easily see in the plots or in the SVisual cut section. Now math is, you can see that we have to write the different type of explorate here. We have to write the relative error control. We have to give the initial value of error, relative error. We have to give the initial value of iterations, not damped. So all these are related to the maths, and it helps to solve the complex equations that are being used in to calculate the above mentioned quantities. Because we have to calculate above mentioned quantities, it can't be like you can't solve all these by hand. So math section basically added in the simulator to help or to calculate all the quantities. Now we can see and we can move to the current plot. So current plot is basically where you have to plot the current values in the form of electric field. You can also find it your potential values as well. Then in the next slide is your most important section is solve section. Basically, in why we are discussing solve section. Solve section is the only section where you can't change the hierarchy of the commands, or you can change the hierarchy of the order of the various commands. So let's see first of all your build up of initial solution. It gives the iteration as first step. Initial guess is to solve which correspond to the specification in the electrode section. Here your convergence is up to 100 iterations are allowed only in the initial solve section. Now the first quasi-stationary statement ramps up to drain voltage 0.05. Now here you are ramping your drain voltage, assuming the initial value, assuming the steady state approximation. Quasi-stationary, you can see the commands that we have write here, that it as initial step is 0.01, minimum step is 10 raised to power 5 minus 5, and maximum step is 0.2. So you can change these steps, but according to your device. You can't change very drastically, but if you want to change, make sure convergence happens, because this step basically leads to the not failure of convergence. Now the next is initial step, minimum step, and maximum step parameters. Basically this control the iterative procedure, deciding how the simulator approaches the final goal. If your first previous iterations are fine, then it will move to the higher speeds. If your previous iterations are not converged, or your previous iterations are not converges at point and giving the again and again giving the error, it will lead to your not convergence value. So it is very important, as initial step, minimum step, and maximum step parameters should be provided very accurately. Similarly, the second quasi-stationary statement ramps the gate voltage. Now we have already ramped the drain voltage. In the quasi-stationary second command, we will ramp the gate voltage, that is 1.5 volt where we have provided. The step size is augmented automatically or reduced if your last previous step is not converged properly. Now it will be incremented if your previous step converges properly. So this is happens as kind of loop. So we can see that in quasi-stationary, initial step size is 10 raised to minus 3, minimum step size is 10 raised to minus 5, and maximum step size is 0.05. So we can see that if the step size has been reduced to value smaller than minimum step size, the sweep will be terminated, and the conclusion is that your simulation has been failed. So when you are defining solve section, and mind it, whenever you are defining solve section and your sweeping is terminated or your simulation is terminated, then go and check your initial steps. If it is smaller than minimum steps, it should be increased or decreased accordingly. However, you can't give the minimum step more than maximum step, and you can't give the minimum step less than initial step. So it in between you have to give. Now the solve section does not only provides the ramping for this boundary conditions for electrodes also, and also it provides the ramping for various parameters that are being even in the material properties. Like in the Quasi stationary, you can see provide material interface, that is aluminium gallium arsenide / indium gallium arsenide, and the model is basically surface recombination model. Okay, and here the parameter that you want to ramp is parameter S not E, and in at what value you want to ramp it is 10 to the power 5. Same the example of an ambient temperature ramp, which is you want to ramp this value up to 400 Kelvin. So yes, solid section is little bit confusing, or you can say little bit tough section as compared to the other section, because here we have to keep the hierarchy, we have to keep in mind like minimum step, initial step, maximum step, and we have this solve section also turns out to be the like convergence problems. So we have to keep study this section very carefully if we want a smooth simulation. Now I would like to discuss about some parameter files. Now parameter files has material, basically different type of model parameters of various materials. Now these files can be easily generated like minus Sdevice -p. I will generate this file. So you can see here we have typed Sdevice -p, and it gives the all the parameter file that is being associated with the all kind of materials. It's very long file. You can easily generate this file using the Sdevice -p. Now all the other material files, single material files, you can easily generate like -s, -p, material, which kind of material you want, like which material you want, material model parameters you want, and which kind of like you already used or library you want. So all these files can be easily extracted from by using Sdevice parameter. So if you have write this file, you have noted that how to write this file, you can easily create your own CMD file easily. The most important factor is you have to give the exact input files. The name should not be changed. If it is _des.cmd, it should be like same. If it is _des mesh file, it should be the same mesh file. The names can't be changed. If your names has been changed, it will not call those files. So it creates the error. So if you are getting these kind of error, please go and check. Now second most important, which most people do the error thing, is that solve section. Solve section is very important section for convergence of your CMD file. So kindly go through this video and check your solve section as well. So it will definitely help you. Thank you. Thank you so much for watching my video. Thank you. Have a nice day.